Hi, in this video we are going to learn about the unit circle. But before that, let's remember the trigonometric ratios. So for a right angled triangle where one of the angles are given like this, and let's say this is A, this is B, and this is C, we can write down according to the given angle. This side is the opposite angle, and this side here is the adjacent angle, and always the side across the 90-degree angle is called as the hypotenuse, right? So basically, the trigonometric ratios are like sine of alpha is equal to opposite over hypotenuse, right? And cosine alpha is adjacent over hypotenuse, right? And tangent alpha is defined to be opposite over adjacent. Now, so far, we know that we can calculate the sine of angles bigger than 90 degrees, right? For example, we know that sine 120 degrees is root 3 over 2, or sine 150 degrees is 1 over 2, or cosine 120 degrees is 1 over 2, and so on. Now, how come we can calculate the sine, cosine, or tangent of angles bigger than 90 degrees? Doesn't it sound weird for you? Because when you look at this right-angled triangle here, we don't have much of a choice in terms of the measure of the angles. Now we have two acute angles here, and the biggest angle being the 90-degree angle, right? So my point is, we can only calculate these trigonometric ratios in a right triangle here up to 90-degree measure, right? So how come we can calculate the trigonometric ratios with the angles bigger than 90 degrees? Because we have the unit circle, which converts the trigonometric ratios to trigonometric functions, right? So let's see how. So this is the unit circle. Now this is called as the unit circle because this is a circle with the radius being 1 unit. So here the coordinates are 1, 1, -1, and -1, because this is negative x and negative y axis, right? But the radius, it doesn't matter where you draw it. You can draw the radius from here, you can draw the radius from here. It doesn't matter where you draw it. The radius is always 1. So this is the unit circle. So we know from chapter 2 that if we were to write down the equation of this circle, because the center is the origin, we would be writing it like x squared plus y squared is 1. So from here we can say that the center is 0 to 0 and the radius is 1, right? So this is the unit circle. Now what happens is, if we draw a radius from the center to any arbitrary point on the circle, let's call that point P with the coordinates x and y, right? And if I just draw this line, which is perpendicular to the x-axis, I will have the same right triangle that I just drew to remind you the trigonometric ratios, right? So let's now write down the trigonometric ratios accordingly. Now, if this is the angle theta, then across the angle theta is the opposite side, and this is the adjacent side, and of course this is the hypotenuse as it's across the 90-degree angle. Now let's write sine theta. Now sine theta is opposite over hypotenuse. Now the opposite, this side length, is basically the y coordinate, so I write y, and well, the hypotenuse is the radius is 1, so I write 1. So basically sine theta is y, right? So cosine theta is adjacent over hypotenuse, right? Now adjacent is the x value here, right? The x coordinate. So I'm going to write x over hypotenuse being the radius, which is 1. So actually, this is just x. So, as you can see, I can now write the coordinates of the point P not like x and y, but rather like cosine theta and sine theta all of a sudden, right? Because cosine theta, I just calculated it to be x, and sine theta is y. So instead of writing x and y, I can now write cosine theta and sine theta as the coordinates of the point P. Now you can remember this order from here. Now the coordinates are in alphabetical order, and you can see that the trigonometric ratios are also in alphabetical order, right? So some books also refer, going further, that this axis is no longer x-axis but cosine axis, and y-axis is no longer y-axis, it is the sine axis, right? This is when we convert the trigonometric ratios to the trigonometric functions, because now those trigonometric ratios are coordinates of a point. And once I start defining the coordinates of points in the coordinate plane with trigonometric ratios, I'm not talking about trigonometric ratios anymore, but trigonometric functions. Now, here's a rather more interesting fact. We write the tangent of this angle theta to be opposite over adjacent, where opposite is the y coordinate and adjacent is the x coordinate. So if I write it like y over x, then I end up with y being sine theta, whereas x being cosine theta. So the relation between tangent, sine, and cosine are thus formed, right? So tangent theta is equal to sine theta over cosine theta. Now this is called as an identity, right? And another identity would be that the radius is 1. So we can say that if you write the Pythagoras theorem, x squared plus y squared must be 1, because this is the x value, this is the y value, right? Now, if I change x and y with cosine and sine, then it becomes cosine squared theta plus sine squared theta is 1. So this is another identity that we'll be using in P2, right? And this applies to all triangles that you can draw inside the unit circle. So you can draw this radius and you can have a triangle here, it will work. You can draw this radius and you can have a triangle here, it will work also. So regardless of the radii drawn, this identity as well as this one works perfectly. So if we sum up, the unit circle is a circle with center, the origin, and the radius 1, right? And if we have this point with the coordinates x and y, we can also express these coordinates as cosine theta, sine theta. And theta is the angle between the radius drawn from the center to the point P and the x-axis, right? And what happens is we just move this point anti-clockwise around the unit circle, right? So that we can change the angle theta, thus we can change these coordinates and we can get trigonometric functions. From this triangle we get the following. First of all, just because cosine theta is x and sine theta is y, if I write down the Pythagoras theorem, like x squared plus y squared equals 1, I end up with cosine squared theta plus, not y, sine squared theta is 1. This is my first identity. And the second one is the ratio between opposite and adjacent, which ends up with tangent theta equals sine theta over cosine theta, right? These are the two identities we will use frequently in this chapter. Now, I want to close this with a short video that shows the relation between the angles in the unit circle and the graph of sine function, right? And then we're going to go on with the second part of the unit circle. Now, when the coordinates of the point P changes, the y coordinate, which is a sine value, right? The sine values form the sine graph. So you can see that one full circle, one full round, gives us one period of the sine graph. And after that, it repeats itself because, well, we start from the beginning on the unit circle in a full round again, right? So this is the relation between a trigonometric function of sine and the unit circle. In the next video, we will start using the unit circle in our calculations. And we will also see some interesting relations between those trigonometric ratios. Thanks for watching.